Alright guys, let's begin our adventure with 9.3, rational functions and their graphs. We have three examples that we're looking at today. We're going to be looking at points of discontinuity, vertical asymptotes, horizontal asymptotes, and a lovely little thing called a hole in a graph. Right? So, let's begin with looking at the definition of a rational function. Just trying to jump right on in. A rational function is any function that can be written as p of x divided by q of x. So basically, a function divided by another function. And as you can see, the domain of f of x is all real, except for those which cause the function in the denominator to be equal to 0. All right, so you have these lovely graphs in your textbook that you can take a look at. And one thing you need to know is this term, point of discontinuity. That is going to be any place where you have an asymptote or a hole, a place where your function is not defined for that specific value for x. Okay, so graphs are either continuous or they might have a point of discontinuity. All right, example 1, finding points of discontinuity. Pretty easy, to be honest. You set your denominator equal to 0 and you solve for x. So that means you're either factoring, using the quadratic formula, anything that you can do to solve for x. Most of the time you're able to factor. Some of the time you're not, and you have to use that quadratic formula. So you see, factoring is important, and so is that quadratic formula. So now let's take a look at these two for your notes. The first one we have, y equals 3 over x squared minus x minus 12. Okay, so the only place that could cause a point of discontinuity is if the denominator is equal to 0. So you have x squared minus x minus 12 equals 0. This is a trinomial, and it's a quadratic trinomial. And I know that there are factors of negative 12 that when I add them together would give me a negative 1. In this case, that would be x minus 4 and x plus 3, right? Because 6 and 2 would give me 4. So not going to work. 12 and 1 would give me 11. All right, so now using the zero product property, again, term from the past, we set each of these equal to 0, and you solve for x. Now, you don't have to go to this extent, because I know many of you are quite intelligent and would be able to do this without actually breaking it down like this. So when you have it written down like this, if you want to say your points of discontinuity are when x is 4 and when x is negative 3, perfectly okay with that. Okay, this is just your breakdown of how you do it. Okay, so we have points of discontinuity at x is 4 and negative 3. Now let's take a look at the second one. So again, you're looking at just the denominator. The numerator has absolutely no impact on the point of discontinuity. 3x squared plus 4 equals 0. So you want to subtract 4. 3x squared equals negative 4. Divide both sides by 3. You have x squared equals negative 4/3. And right about now, you should be getting a tingling sensation. Something doesn't seem right. When we take the square root of both sides, what happens when you take the square root of a negative? You end up with an imaginary number. So this one, there is no real solution, so there is no point of discontinuity, right? So if when you break it down, there's no real solution, then there's no point of discontinuity. All right, let's take a look at this second example. But before we do that, let's take a look at a few images from your book. All right, so there are some points on this graph, like we just found in example 1, where you have those points of discontinuity. If there are two different kinds, you can either have a vertical asymptote or you can have a hole, right? So a vertical asymptote is created when you have no corresponding expression in the numerator. So looking at this top one, you have vertical asymptotes at x is 1 and x is negative 2. Then looking at the second one, you have a whole because you have a corresponding expression in the numerator and the denominator. So this would cancel out, leaving you with y equals x plus 1. But you can't just ignore the fact that that x minus 2 was part of the original equation. So then you have a whole at x is 2. Look over at this graph. So they graphed y equals x plus 1. The y-intercept is 1, your slope is 1, so you go up 1 to the right 1. But you have a whole when your x is 2. All right, well, we have a possibility of having a whole and a vertical asymptote. And so this x minus 2 would create a whole at x is 2. But when you simplify that, you would have y equals 1 over x minus 1. So now graphing that y equals 1 over x minus 1 results in this. But you, again, cannot ignore that you have a whole at x is 2. So that's what this is representing. And then last but not least, you have a situation where you could potentially have, x minus 2 over x minus 2, x minus 2, for example. And so this would create a whole. And if you cancel those out, you have 1 over x minus 2, and that would give you a vertical asymptote. However, you can't have a whole and a vertical asymptote at the same place. The whole is more powerful. I apologize. The vertical asymptote is more powerful, if you will. Not really that either one of them has power, but I've seen a lot of superhero movies here lately. But the vertical asymptote maybe takes more space. So therefore, if you have a whole and a vertical asymptote at the same value of x, the vertical asymptote is going to supersede that. All right, so now let's see these examples. All right, so excuse me. Describe the vertical asymptote and whole for the graphs of each rational function. All right, so looking at A. So we have x minus 7 in the numerator, x plus 1, x plus 5. This x minus 7 doesn't match anything down below, so I don't have to worry about any holes. This is only going to be vertical asymptotes, and you're going to set each of those expressions equal to 0 and solve for x. So x plus 1 is 0. X plus 5 is 0. Subtracting 1, you have x is negative 1. Subtracting 5, you have x is negative 5. So we have vertical asymptotes at x is negative 1 and negative 5. All right, moving along to B. Well, we have this x plus 3 over x plus 3. Well, that's going to create a whole. And see how that circle mimics a whole? That kind of helps. So if we reduce that, we're left with y equals x, but we can't ignore this. So then you have a whole at x is negative 3. And we got that because you set it equal to 0, and you subtract 3 from both sides. Okay, and then let's take a look at this monstrous looking one here. We have an x plus 9 right here, and we have an x minus 6 here. Okay, all right, so this would simplify to just 1 over x plus 9, which gives us a vertical asymptote. Oops, forgot that part of the B. When x is negative 9. But we know that these are creating holes at x is negative 9. Hold up, wait, that's what that is. So there's no hole there. So that one's just gone. And then x minus 6 equals 0. Well, if x minus 6 equals 0, then you have to have x equals 6. So we have a vertical asymptote at x is negative 9 and a hole at x equals 6. All right, now let's go ahead and take a look at the final example that we have. But before we do, I want to review the summary box from the textbook. But the thing is, the summary box from the textbook is a little bit cumbersome, so I tried to cut it down to this to make it as easy as possible for you. The first one, we have a degree of a denominator is larger than your horizontal asymptote is y equals 0. If the degrees are the same, then your horizontal asymptote is y equals a over b, simplified of course, A representing the leading coefficient of the numerator, B representing the leading coefficient of the denominator. I'm trying to speak too quickly. And finally, the degree of the numerator is larger. If the degree of the numerator is larger, then there is no horizontal asymptote and one less thing to worry about. All right, so let's take a look at this. So we have three possibilities. Degree of denominator is larger, horizontal asymptote, y is 0. Degree of the numerator is larger, no horizontal asymptote. Degrees are the same, then it's just the coefficients of the leading, then y equals a over b. Okay? I'll just say it like that. Okay, so now taking a look. You have find the horizontal asymptote of y equals negative 4x plus 3. So, doing that, we see here that the degree is 1, because that's x to the first power. You know what? So is this one, because that's degree 2x to the x to the first power. So the degrees are same. So then you are going to look at just your leading coefficients of the x term. So then your horizontal asymptote is going to be y equals negative 4 over 2. Negative 4 over 2 simplifies to just negative 2. So you have a horizontal asymptote at negative 2. See, not too bad, but it really does help to know this. And it's really easy to get some of these turned around. So please just be careful and make sure you're reviewing these. Please let me know if you have any questions. Have an awesome day.